Good morning. Welcome to today's webcast, Controlling Costs and Prioritizing. I'm Mike Rhodes, Managing Editor of Hydrocarbon Processing, and I will be your moderator today. Gas systems can easily become an afterthought, especially if they are not transporting anything overtly hazardous. Yet even the most mundane gas leaks can add up to serious cost when they drive down the efficiency of equipment or lead to outright downtime. Specialty gas leaks are an even bigger problem. At best, they are expensive, and at worst, they are downright dangerous. So, what do you really need to know and do to keep your gas systems operating effectively? Joining us today is Jeff DeWitt, Applications Engineer from Swagelok, Research and Development, and Thermo Fisher Scientific as an engineer and project manager for new product developments, where he led the application collaborative products team within Swagelok's manufacturing and assembly operations. Jeff then capacity projects in manufacturing and assembly, in high purity cleaning, technical cleanliness, and supporting infrastructure systems, including facility power, deionized water, and industrial process gases. Currently, Jeff serves as an applications engineer, where he product manages the Swagelok gas distribution program. He graduated from the University of Akron with a Bachelor of Science degree in mechanical engineering and from Baker College with a Master of Business Administration. Okay, just some general housekeeping notes before we get started. Following this presentation, we will have a short question and answer session. You can participate in the Q&A session by asking questions at any time during the presentation. Just type your question into the Q&A box located on the bottom left corner of your screen, then click the Submit button. Please take this time to familiarize yourself with the webinar platform. At the bottom of your screen, there are multiple application widgets you can use. All the widgets are resizable and movable, so feel free to move them around and get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. The slides will advance automatically throughout the event. If you are experiencing problems with the program, please press the F5 on your keyboard to refresh the presentation. You can also visit the webcast help guide by clicking on the Help button below the slide window. I think we're ready to get started. I'm going to turn the time over to Jeff.
Thanks, Mike. Thanks for the nice introduction. And, grateful for everyone to be joining us today. The one bit that I would add to my introduction there is only that, probably like many of you, I've been responsible for helping to manage a lot of capital projects and projects that seek out operational cost saves, and been responsible for both managing and tracking those cost saves, as well as helping to realize some imperative safety efforts and helping to manage enterprise risks. So I think that will lend itself nicely to the content that we have over about the next 50 minutes or so. The intent for today's webinar is for it to be informative. Like Mike alluded to, the theme for today is that these gas distribution systems within many of the organizations and customers that we reach are often overlooked and underappreciated. This results in both considerable risk and honestly, some unwanted waste for many of our customers. My hope is that at the end of this presentation, you, as a valued resource within your organization, will be able to articulate some of these key risks for both personnel as well as your environment, as well as some of the cost savings and cost management opportunities. My hope is that you can be an advocate for the improvement and ownership of these systems. Today, we're going to break a little bit into the DNA of these gas distribution systems. We're going to talk a little bit about background, but then really get into a high-level risk assessment, where our goal will be to understand some of the best practice mitigations. From there, we'll dig into the cost management of these systems, and really with the intent of looking at the total life cycle. And then, time permitting, we will get into some of the Q&A. A gas distribution system is defined as a network of tubes, pipes, and a lot of other components that are used to transport a gas, typically from a high variable pressure source to a designated controlled point of use. In this example, we have a laboratory where the point of use is within, sorry, I have an overhead announcement going on. The point of use may be our laboratory equipment, and then the source gases come from the outside. So in this case, they're stored within the bottles on the outside of the environment. A gas distribution system can serve a variety of functions, but at minimum, it needs to ensure that personnel can access the gas bottles so that they can be adequately replaced. At its core, a gas system is really intended to help deliver a high variable pressure to a low constant point of use, as we've mentioned, in a very uninterrupted manner. And the neat thing is that these gas systems are capable of handling both reactive, toxic, and corrosive gases, as well as fiduciously handling your high value, high purity gases. Gas distribution systems can be found in a variety of applications and in a variety of industries. But one thing that we see that's kind of unanimous across all of these is that there's always opportunity to where these systems are overlooked and misunderstood. What we see among our customers is largely that those who overlook these systems on a regular basis fall into one of four paradigms. Sometimes ownership is not routine, meaning you may have like a facilities or an MRO team that handles your pedestrian gases, compressed air or nitrogen, low cost stuff. But then you have specialty gases that are owned by, say, like a laboratory manager. And where the ownership is maybe not routine or not typical, sometimes these systems fall through the cracks. In other cases, we have a utility that may span multiple jurisdictions and ownership is not clear. In other circumstances, we see that these systems are simply deprioritized. And in some cases, it's because there's higher priority activities. In other cases, it's treated as more of like a foundational utility, like it's just taken for granted. And that fits in with the last paradigm, which is kind of that set it and forget it, where it's often overlooked that gas distribution systems need some TLC and need some regular maintenance and oversight. So today we're going to dig into both the safety risk assessment as well as an opportunity on cost and cost management for these. As we jump into our risk assessment, it's important to first look at some of the potential adverse consequences to both personnel and environment around gas distribution systems. When they fail, at its core, the risk is that a hazardous pressure, temperature, or media escape and it cause adverse impact for your personnel or environment. Another potential consequence, or really a cause, is that with pressure reducing devices like regulators, it's possible that they fail, resulting in an overpressurization either upstream or downstream of that regulator, contingent upon regulator type, where the equipment, either upstream or downstream, may or may not be capable of handling that pressure, temperature, or media. It's also possible that we may be carrying a specific type of hazardous media, like a flammable media, where when that escapes, it can cause other risks for people and environment. Or it may be possible that we're carrying an oxidizer, where that media, independent of escapement, could ignite given the right conditions. So all of those things can be bad for people and environment. Before we get into our first risk, though, we got to do a little bit of an education on pressure reducing regulators. In the shot we have in the lower left-hand corner, we have a basic cross-section of a regulator where a high pressure is brought in from the left and it exits out at a low pressure, shown in blue, to the right. Now, the place in the regulator where the magic happens, where the actual pressure is bled from high to low, is at this interface between the seat and the poppet. Should something jeopardize that interface, that interaction between the seat and the poppet, we could have an undesirable consequence. That consequence is referred to as regulator creep. And the symptom that we observe is that the outlet pressure, which typically is in blue, is at that low level, will increase over time to suddenly be at that state of the high pressure input. And that can be very detrimental for equipment or people either upstream or downstream that expects and is otherwise designed and built for that low pressure. The yellow arrow shown here is really just a reminder for us. We're going to talk a little bit about that very thin membrane. It's referred to as a sensor element here in a bit. So the look of this slide and the next few slides are going to be very similar. We're going to be talking a little bit about risks, and we're going to start with opportunities for design in the way of these gas distribution systems. So with all risks, we start with an oversight. The oversight allows for certain failure modes to occur. As a consequence of those failure modes, there are undesirable consequences. The same consequences that we talked about earlier. There's some color coding. The red and the blue coincides with what's shown on the watermark on the lower left, and it's consistent with what we talked about before. Now, to avoid those risks, those consequences, there are certain inherent mitigations that we can design into the DNA of our gas distribution system. So in our first oversight, we have an oversight for regulator creep built into our gas system. This can result in a problem when the seat becomes contaminated or that interface between the poppet and the seat is jeopardized that will result in a downstream pressure rise. It's also possible that we have some regulator misuse, and we'll talk about that here in a sec. In the lower illustration, what we have is a basic pressure reducing regulator where input, a high pressure, comes in from the left and it exits out the right as a low pressure. We have two pressure gauges straddling our pressure reducing regulator, and we have a ball valve downstream of the pressure reducing regulator separating our regulator from the point of use. The first mitigation we can deploy to help reduce the risk of regulator creep includes adding a relief valve downstream of the regulator. And that the value of that is simply that if the pressure should rise or increase, we can bleed off excess pressure without it risking the equipment downstream. Another convenient lever is that we can deploy an upstream ball valve. That upstream ball valve offers value in that it helps to reduce regulator misuse. Some customers we see believe that a pressure reducing regulator can serve as a valve. And for all intents and purposes, it's designed to close. But for risk of regulator creep, it's highly recommended that an upstream ball valve be leveraged instead, and that encourages the right behaviors. We can also install an upstream filter to that regulator to catch any contamination before it does bad things to the seat, like it's done in the illustrations above. And last but not least, we can deploy a simple vent valve in between, behind the regulator and in between the two ball valves, so that we have the capability of relieving pressure once those valves are closed and servicing either our regulator or filter. Now, conveniently, many gas distribution systems will be built with like a small subassembly, since these components are all kind of conveniently packaged, or built onto a panel. It's also possible that we can pick a seat, a softer, more compliant seat that will be more robust to that creep risk. This yellow arrow are simply to remind us that we're going to talk a little bit about some of these other features here in a later slide with some of our other risks, taking special stock in where the relief and the vent valve discharge to, as well as the value of having a slow open valve on the upstream of our pressure reducing regulator. My comment to you would be, I highly encourage you all to take a look, walk out to your facility, walk out to your plant floor afterwards, after this webinar today, and take a look at your regulators. Take a look and see if you've got these types of mitigations, and really ask yourself, should you? Another design oversight in the way of adequate consideration for media involves design for flammable media. In this case, we'll talk a little bit about hydrogen. Hydrogen is dangerous because it is flammable at a wide range of applications, or concentrations. But hydrogen is especially problematic for gas distribution systems because it is a small molecule and it is a very friendly molecule, and that can cause some problems. The best analogy I've ever heard for hydrogen is that it's a lot like glitter. It has this propensity, it's small, and it has this propensity to get onto everything and stick to everything. And that's exactly what it does to to a lot of the steels that we use in our gas distribution systems. The hydrogen has a way of working its way into some of the imperfections in the material, the cracks, the grain boundaries. And what that results in is a phenomenon known as hydrogen embrittlement, where it makes the material more brittle. And that has a propensity to lead to eventual component failure, early component failure. And that can cause undesirable consequences. Certain stainless steels that we select for our gas distribution systems can be more robust to hydrogen embrittlement in general. And there's a lot of topics on this that I could speak to, but generally stainless steels with nickel concentrations greater than 12% tend to be more resilient to hydrogen embrittlement. Another risk or failure mode behind hydrogen is inadequate consideration for permeation. Permeability is the measure of how easy it is for a small molecule gas to leak through some sort of membrane. And in the case of a gas distribution system, we have to pay special attention to the organic materials that we choose. I think of things like hose cores, O-rings, and or like valve seats are some of those things that we need to pay special attention to ensure that we don't have excess permeation. It's also worth noting in this illustration here in the center bottom that yes, hydrogen will permeate out of a membrane, but it's also possible that the outside environment, which is not typically hydrogen but other stuff, it also has the equal propensity for creeping its way inward. Another inadequate consideration for media involves consideration for oxidizer medias when it comes to gas distribution systems. So in this case, we'll talk a little bit about oxygen. Oxygen is a problem because it can ignite given the presence of both a heat and a fuel source. And that can happen at very low concentrations. Admittedly, 16% or greater oxygen concentration percent by volume is enough to cause ignition. The air we breathe is greater than 16% concentration of oxygen. There are other oxidizers too that we won't hit on, but are still equally at risk. Fluorine, nitrous oxide, ozone, to name a few, where the primary failure mode of an oxygen system is that we allow for the presence of that heat and fuel source to complete the triangle. So at its core, the mitigations involve adequate material selection so that we can minimize the fuel source. In the case of an oxygen system, a conventional stainless steel like we might choose in normal cases is really not ideal because it does serve as a fuel source. So in this case, what we've done is we've built a gas distribution panel, but it's constructed from brass in lieu of the stainless, which serves as a fuel source. Another source of fuel could be the contamination that is present on the gas distribution system when it's constructed. That contamination can be mitigated by using ASTM G93 certified components. ASTM G93 is just an industry standard around oxygen service, and it ensures adequate hydrocarbon and particulate cleanliness as to mitigate that fuel source risk. Now, in the way of heat sources can come in a few manners. It can come from the friction within our gas distribution systems, but it can also come from things like adiabatic compression, which is what happens when we see a rapid increase in pressure. We also see a immediate increase in temperature, and that can be enough to cause ignition. But also we can see particle impaction. And this is an event where we probably had like a contaminant, like some of that like little stainless steel flakes that we saw on our seat from an earlier example, and it gets accelerated through our gas distribution system, smashes into the inside wall of a fitting in this case, which is a stainless steel fitting, and that was enough to cause ignition. So we can deploy nice little tricks like making sure that we don't create particles in our gas system. So that comes down to, again, material and component selection, as well as leveraging proper filtration to catch some of that stuff before it does bad things. There's a couple other generic design oversights that I'll speak to quickly around gas distribution systems. Probably the most prevalent oversight we see is really an inadequate component selection. let's face it, there's a lot of parts out there. Anybody who looks at a product catalog, it's usually overwhelming. And it's really easy to lose sight of what's important given the fact that we have materials and flows and pressures and temperatures and media compatibility, all that stuff. So in order to mitigate that risk and the subsequent failures that come along with it, we highly recommend reaching out to the right resources, internal resources, external resources. There's a lot of great knowledge out there that is at our fingertips. Also leaning on standardized designs, whether it's designs that are proven within your organization and or for your applications, or leaning on like pre-engineered, pre-standardized systems. Those are very effective for handling and helping to mitigate risks around some of the unique medias and pressures and temperatures that we see. Another oversight that's very common is inadequate consideration for where our vent or our relief valves vent to. And this is important. That goes back to the earlier schematic. If we have a hazardous media, a flammable media, or an oxidizer, chances are likely we don't want to see it dispelled into the general environment where our people could be potentially at risk. So whether we're venting to a safe roof line or to a containment area or even to flare, that's really paramount, and that's something that we see more often than not. Lastly, permeation, not just for hydrogen in our earlier example, but permeation of a hazardous media can be risky. So adequate consideration for some of the organic materials that are at risk for permeation is paramount. Beyond design, there are risks that we inherit or can be exposed to during the assembly, test, and installation of our gas distribution systems. At its core, these failures happen when we don't adequately pull down the components, assembly of the components is inadequate, and we fail to appropriately and safely test prior to full pressurization. And this can have a sequence of undesired consequences. I've seen fittings not properly pulled down with full pressurization. I've seen tubes bend over backwards and fire ferrules and nuts into locations where they're never found again. And lucky for me, I've never seen someone actually get hurt, but it's very possible. So we have certain tools, mitigations that we can deploy to help catch and prevent these things from happening. We can rely on basic leak inspection. So whether it's a soap and water combination, or if we've got a nice little pre-assembled unit that we can stick onto like a helium leak tester if we have concerns for some of that smaller media that's of high value. We can do mechanical fitment checks to make sure that we've adequately pulled down the fittings through gap gauging. I've seen a lot of organizations deploy checklists, or this is one of my favorites. I've seen pipe fitters and plumbers initial some of the fittings that they've done in Sharpie so that they know that they've pulled it down and that they've done the gap gauging. It's kind of a nice check and an easy to audit. Also, leaning on pre-assembled panels or pre-assembled systems is very useful. Let's face it, a system that's built in a contained environment that's free from distractions, like the distractions of otherwise building it in situ on the shop floor where it's noisy, greasy, loud, you're much less likely to observe those human error that might otherwise come and result in some of these risks that we speak to. The last opportunity certainly lies in the way of leveraging installation oversight. So whether you have a buddy system where you have someone pulling down a fitting, or you have a tradesman pulling down a fitting and then someone goes through and audits it, or there are organizations that will offer you that same sort of oversight should you so choose to deploy it. One of the most common organizational shortcomings that we see with gas distribution systems, as we've kind of talked about, is the lack of ownership and sustained oversight of these systems. One of my favorite sayings about gas distribution systems is that these are often the types of systems that, like they're loose change, they fall between the couch cushions. And when it comes to the change that's at risk here, it's not just from a safety standpoint, but it is about cost, which we'll get to here in a moment. So in order to mitigate those risks and some of the undesired consequences, which is, let's face it, there's quite a few, we definitely recommend that organizations have clearly defined ownership for these gas systems. Typically, this is cross-functional ownership, where the accountable parties, the people that everyone answer to, are conventionally resources like a plant manager or an MRO manager or a facilities manager, a lab manager, someone with some sort of oversight that can watch the breadth of the responsible parties. From a best practices too, having standardized work instructions for maintaining this equipment is paramount. Some of the gold standard organizations, customers that we see, a lot of them will leverage their MRO systems for like automated maintenance minders, so that they can ensure that their preventative maintenance is following the desired cadence that they're after. And the thing that unanimously works is relying on regular audits for these gas distribution systems to make sure that there's not just good safety, but stewardship of resources. Speaking of fiducious use of resources, we now jump to controlling of costs. If you talk to anyone in your finance team, you would find that typically opportunities for controlling costs fall into three categories: cost savings, cost avoidances, and revenue preservation. Now, cost savings are things that honestly go right back into the profit for an organization. They're costs that are historically always been in our rearview mirror, and if we can stop paying them today and tomorrow, then it goes right back into our profits. It's no different. Cost avoidances, however, are things that we maybe don't typically see, but should we have a failure of a gas distribution system, there's definitely going to be a need for some cash or capital outlay to help remediate that failure. Last but not least, revenue preservation is equally important and often bucketed into this cost controlling opportunity. Let's face it, if we're not pulling in revenue, we're probably not making a profit. Now, what we'll do over the next couple slides is talk a little bit about the system life cycle of these gas distribution systems and opportunities for controlling costs in both the design and commission, as well as the operate and maintain stages of the life cycle. Since we started off with safety risk assessments, it only seems appropriate that we first start our conversations on safety. So what I'm going to do is share some statistics from the United States. My apologies to anybody who's joining us internationally. And by sharing these risks, some of these stats, I'm not at all trying to take away from the emotional toll or physical toll that those associates who deal with a workplace injury have to pay. But I do want to point out that there is a dollar value, there is a cost to organizations in the way of an avoidance by seeking to avoid these injuries. The first stat there on the left, $44,000 per medically consulted injury in 2020. That's a number I hear all the time. Every time I seem to engage an environmental health and safety professional, they always seem to be able to cite that figure. And the scary thing is that number's up over 10% from the last time I heard that figure, kind of pre-pandemic. And certainly that number could be worse, contingent upon the severity of a gas distribution failure. Now, the stats on the right are really telling. Look at that. In 2020, in the United States, there were over 99 million lost working days. For anybody with a calculator, that amounts to over 271,000 years. That's 271 millennia of lost work in 2020. And doing the math, there's 149 million working Americans in 2020 estimated per the US Department of Labor. That amounts to 2/3 of a lost day per working American. So when you go walking down on your plant floor and you say hi to all your friends, think about this one. Every one of those people you smile and say hi to, that's 1/3 of a lost day per 2020 stats. That's amazingly high, and you can imagine the amount of cost that imparts, so the cost avoidance opportunity for organizations. The environmental reparations can also come at a steep cost or a cost avoidance for organizations that are found to be in violation. These cost avoidances can come in the way of things like financial commitments from organizations who are found to be out of compliance and need to bring their systems and their facilities back into compliance. There are recovery costs or penalties for those who are in clear violation, and there can even be incarcerations for those gross violators. So it's important to note that none of these stats for the US EPA in 2021 tied directly to gas distribution systems, but it doesn't mean that they're excluded from that. A big opportunity in the way of cost avoidance when it comes to gas distribution systems involves the use of pre-designed, pre-engineered panels when building or replacing your system. And these offer a lot more than just the convenience of avoiding, and freeing up some of the labor and engineering resources to do it. Let's say, for example, we have a relatively pedestrian pressure reducing panel, like shown on the lower right here. This panel flows from bottom to top. It includes a regulator at the bottom. It's got a couple gauges that straddle that regulator. It's got a vent valve to the lower left, a relief valve to the upper left, and then an isolation valve at the exit, all built on a stainless panel. Let's say hypothetically that we know the pressures, the temperatures, the medias, the flows, and all the necessary safety mitigations that we want to build into that. We're like ready to pick parts. Well, it turns out there's actually quite a bit of engineering value built into that pre-designed, pre-engineered panel. There's also a lot of convenience in the way of labor avoidance when it comes to managing the inventory should alternatively you seek to build it yourself, right? There's less packages to deal with. There's less content verification, storing, staging, and the like. There's also a convenience in the way of reduced PO cutting. Let's face it, a PO for most organizations is not cheap, especially if you've got an organization with multiple approvers. Those approvers are generally not cheap to, from an hourly rate. So cutting one PO versus cutting 3 to 5 is a huge advantage here. Last but not least, by either you building the panel yourself or leaning on an organization that typically builds these panels, their labor rates, your labor rates, tend to be much more cost effective over leaning on an outside tradesman, a pipe fitter, a plumber, whose hourly rates generally tend to be sometimes 1.5 to 3 times more expensive. There's quite a bit of cost avoidance there as well. In the aggregate, there's quite a bit of value built into these pre-engineered, pre-designed panels, and that can be a huge opportunity for organizations that look and seek to simplify and seek those cost avoidances. What's really amazing about this is that in this case of this lower example, the lower right, the overall price tag of that panel is dwarfed by the overall value built in. So it's a very useful lever when you know what to look for. Jumping over to some cost saved opportunities, I'd like to speak to one in the maintenance arena. The specific opportunity is the idea of promoting your components to the front of a panel. So if there's a pre-assembled panel like shown on the left, bringing the components to the front offers some value in the way of maintenance labor over the alternative of burying those components behind in the back. Let's hypothetically say that we need to service the filter, which is shown on the lower right. That filter typically is installed at the inlet of our pressure reducing regulator, which is, we have one regulator on the left, 2 on the right. Regardless, the access to that filter or that regulator is much more convenient when picking the option on the left to that on the right, to the tune of an estimated half an hour to 2 hours of an hour of savings in time by choosing the option on the left over the option on the right. So let's say, for example, your maintenance rates are like between $50 to $100 an hour, and you've got multiple of these panels. Well, this can amount to thousands of dollars in savings per maintenance interval. And on top of all that, what's really great about the design on the left is that because the components are easy and visual to see, it's more intuitive how the panel should operate, assuming there's not clear instructions about how to use the equipment compared to the option on the right. Probably one of my favorite cost savings opportunities in the way of gas distribution systems is the leveraging of changeover panels for critical operations. The premise of any gas distribution system, but especially a changeover panel, is to get as much out of the bottle as we can while preserving a critical operation. So the premise of a changeover panel is to have both a primary and a secondary source of a gas, such that as the primary is depleted, a secondary backup source can be deferred to upon depletion. In the case of the option on the left, as we deplete the primary, manual interdiction is required by an operator or an associate to integrate those changes. And then once the secondary source is depleted, we can defer back to the replaced primary source. Comparatively, the option on the right shows an automatic version of this changeover. So in this case, as the name implies, it will automatically shift from primary to secondary, and or then from secondary back to primary as the bottle sources are depleted. What's really convenient about this is that systems of this nature can be configured with alarms and or pressure switches. So pairing that with an and-on light or a stack light, we can have some sort of automated alerts to let folks know that they need to make these changes. Let's look at an example of where changeover panels can offer substantial value. In this case, we have a customer who uses a relatively pedestrian helium for their operations. Pedestrian meaning like maybe 99.8% purity, nothing exotic, not 5, 6, 9s. In this case, the customer receives their helium in the way of a tube trailer, and they get a tube trailer about once a month. And helium is pretty expensive for those who use helium. For those following the helium market, helium has tripled in cost over the last 5 years. And that's due to both high demand, which helium market has a CAGR of over 6%, paired with the fact that we have a very volatile supply. So helium's gone up. Customers paying $175,000 a month for their tube trailer replacement. The trailer would come in pressurized at about 3,000 PSI. The customer, once the pressure hit around 700 PSI, would call their gas supplier and say, please bring me a new truckload. 700 PSI was by design. 700 PSI ensured that the customer had about 5 to 6 days of critical operation. Per the service agreement that the customer has with their gas supplier, they were given up to 5 days to respond. So as a result, 700 PSI was the outgoing pressure. Shown schematically, we have the tube trailer. It would feed into a very basic manifold, where the manifold would toggle over to a very small backup bank while the tube trailer was conventionally being replaced. From there, the manifold would feed a compressor within the customer's facility and an accumulator commo in order to supply the house pressure for the customer at around 1,500 PSI. Swagelok was able to look and see a tremendous opportunity for a basic changeover panel paired with a second tube trailer. By doing that, we're able to demonstrate to the customer that through a primary secondary kind of AB combo, they could get a lot more resources out of their bottle, out of their trailer, and depleting it to a much lower level, leaving less molecules of that very valuable resource in the trailer. And that amounted to a substantial cost saves for the customer on an annual basis. It was like a very attractive payback. And what was equally important for the customer was that it helped them to preserve that critical operation using a very valuable resource. Furthermore, Swagelok was able to really help them with a redesign of their compressor accumulator combination within their facility to help reduce some of the nuisance alarms that they were experiencing. So an awesome example of where changeover offers a tremendous amount of value. Recovery costs are another category of hidden costs within gas distribution systems, and these are definitely considered a cost avoidance. So when a gas distribution system fails, we gotta do something to fix it, and that always comes with a price tag. That price tag will either come in the way of a capital or an expense of investment, and this can take on a variety of forms. Let's say, for example, that we've got some sensitive equipment that relies on a very precise pressure supply. So we've got a gas chromatograph or a gas chromatograph with MS. Typically, those devices require a precise inlet pressure, like 15 PSI kind of max range between min and max pressure. So if we have a failure, like say an overpressurization of that in that gas distribution system, it's very possible that we run the risk of damaging the electronic pressure control module within our gas chromatograph. And we all know that this can be really expensive. Gas chromatographs and low cost usually don't go together in the same sentence. So it's very possible that that repair, along with our gas distribution correction, can take some time and cost us money. It's also possible that while we're out with that gas chromatograph, we may have to defer to an outside lab, which can come with additional expense, with additional cost. Another category of recovery and costs include recovery labor. Let's face it, gas distribution systems are also often considered a critical operation, and they can go down at any time. And that includes weekends and evenings when our staffing is typically less likely to be at full force. And for those folks that have to triage these systems at inopportune times, that can cause some frustration. I offer an example. 3-4 years ago, I was involved with a major nitrogen system upgrade, like an emergency upgrade of a nitrogen system within one of the Swagelok plants. And admittedly, that emergency triage repair took me out of my day job for about a 2-week period while there was a heavy amount of contractor remediation redesign work. And full transparency, I didn't mind helping with repair, but what was frustrating is when I was asked to work on all those long weekends and I missed like my daughter's softball tournament. That's where the frustration crept in. So certainly that comes at some expense. And last but not least, there's deferred revenue. So in the case of that nitrogen system where I was asked to help remediate, it supported operations that amounted to about $30,000 in revenue an hour. So naturally, you can bet that a lot of the management was very on their seat, very interested in how fast we could go. And that deferred revenue was inevitably of high level of scrutiny. My last thoughts in the way of costs come in the way of reputational impact and the final financial implications that this can have for organizations. So for most organizations, their reputation is simultaneously both their most valuable asset as it is the thing that is always at greatest risk. For the consequences that we've already discussed, these can all detract to outward reputation. So to combat this, some of the best organizations, some of the best customers that we see, they do a couple of things really well to help manage this. But the number one thing that they do is they ensure that their gas distribution systems, along with all other critical assets, are involved with very much like an annual risk assessment, where that risk assessment is comprehensive and it's enterprise-wide. And a wide array of cross-functional contributors are involved and contribute to that risk assessment. The risks that they weigh include a variety of categories and are often weighted. They factor in things like human safety, environment, costs, revenue loss, as well as reputation. And full transparency, reputation tends to be the one potential impacted item that carries the most weight. So I've reached the end of what I'd like to talk about. And just to repeat, the main theme that we see in industry across applications as well as broader industry is that these gas distribution systems are often overlooked, misunderstood. And this can result in risks for the customers, risks for your enterprise, as well as unneeded costs. And most importantly, the risk to reputation that this bears for the customers, for the owners. So I encourage you all to, within your organizations, look inwardly at your gas distribution systems and seek out, do you carry similar risks, and where are your opportunities for both safety improvements as well as costs? I offer that Swagelok can provide a wide range of solutions to suit your gas distribution needs. Without a doubt, we offer not just the components, but we can sell pre-engineered panels and system assemblies and solutions to fit your needs. Our limited lifetime warranty is awesome too. What's really neat, though, is we can do much more than that. We offer a wide array of services and expertise with both local representation across the globe, which means that we're probably already in your backyard. Now, pair that with the fact that this global expertise, we can offer insights into industries and applications, perspectives, industry awareness that can help you to see these opportunities that sometimes are so easily looked past. I'd like to thank you all for your attention during today's webinar. A tremendous thanks to Mike and our host for making this possible. I encourage you all to check out swagelok.com or reach out to your local sales and service center to view many of our products, services, and case studies specific to our gas distribution system successes. Thank you all. Mike, back to you.
All right, that's great. Thank you, Jeff. Awesome presentation. For our audience, we're going to transition now to the question and answer portion of our webcast. You can continue to submit your questions in the Q&A box located on the bottom left corner of your screen. Jeff, we've got a bunch of questions that have been coming through. So if it's all right with you, we'll just jump right in.
Yes, please.
So, okay, first question here. Can I add more regulators to my gas system to manage some of the safety risks?
A great question. A question that we sometimes hear. The answer is yes. Anything is possible, but it's probably not going to be recommended. And here's why. The truth is that regulators in and of themselves are really a flow reducing component. They're a restrictive orifice in your gas distribution system. So by adding an additional regulator or regulators, it comes at the expense of flow performance, meaning you may not be able to flow as much of that media as you seek. Flow can also be compromised for pressure, so you'll end up with greater pressure reduction. I'd say that in general, and this is a very basic generalization, our pressure regulators are designed to have at least a 2-to-1 pressure reduction from inlet to outlet in the case of a pressure reducing regulator. So imagine it like this: the more regulators we throw into the system, the more reductions we have to compensate for. And what that can come at the expense of is less utilization of your source bottle. So there's a compromise with everything. Yes, more regulators can help reduce the risk of creep by putting redundancy, but it does come at an expense.
Okay, you're talking about regulators and symptoms of creep. If a regulator does demonstrate those symptoms of creep, does it need to be replaced?
Another great question. The short answer is it does not need to be replaced, and typically instead it can simply be rebuilt. So like we looked at in our view, I'll actually jump to the slide. The maintenance of the, let me push this up to everyone. The seat itself can be cleaned, just like we see the contamination here on the seat. It's very possible that with an isopropyl wipe down process, we can clean up that contamination, and hopefully that remediates the creep event from occurring. If the seat, we observe damage, we can also replace the seat, and that comes in the way of a regulator rebuild kit. Only in rare circumstances do we see enough damage to the metal parts in the regulator to where there's a full replacement. So we generally encourage everyone to seek a rebuild first.
Okay, that's great. Here's another question from our audience. What are best practices for my servicing oxygen system to avoid safety risks? Sorry, there are some typos in there.
No worries. Yeah, I'd say, like we talked, the name of the game with oxygen is cleanliness. And, the objective is to avoid both oil contaminants as well as any solid particulate like metal contaminants. So starting with clean components is the first step, right? Like if we have any replacements, we need to make sure that we're dealing with SC11 cleaning, or like ASTM G93 cleaning is paramount. And or starting with cleaned bag tubing is also very useful. Being careful to not contaminate the work pieces with either our hands, allowing for the environment to cause contamination, or even our tools. One of the common mistakes we see is like that same wrench that services everything on your shop floor also services your very clean oxygen systems. So making sure that the tools are wiped down is paramount. Using nitrile gloves or something to keep the oils from being deposited from your hands onto the workpiece is paramount. And even leveraging good deburring techniques when it comes to tube cleanliness is important. So bagged tubing is really awesome, but if we've got to cut it, making sure that we've cleaned out, IPA wiped out the bore of the tubing. And just in general, if we're walking away from our work area, keeping the materials covered so that particulate and the environment don't contaminate it is a great start.
Okay. Next question. How do I know if I need 2 serial regulators in my gas system to step down pressure from supply to place of use?
Boy, another great question. And I think it was partly answered before in what we said. So 2 regulators are typically recommended when we need to manage a phenomenon known as supply pressure effect. Now, there's a consequence to using a second regulator. As we mentioned, it comes at the expense of flow, right? We have the risk of reducing our pressures or having greater pressure drop or reducing flows. Supply pressure effect is a phenomenon where as a pressure reducing regulator sees a drop in its inlet pressure, the outlet pressure will increase by some percentage of the drop in the outlet pressure. Let's say, for example, we've got a pressure reducing regulator that has seen a 2000 psi drop in inlet pressure. Now that regulator, let's say hypothetically, has a 1% supply pressure effect, which is an inherent property of the regulator and comes at the consequence of many details of the nuances in the design. We might expect that the outlet of that regulator, 2000 psi drop, 1%, we might see a 20 psi rise in the outlet. So again, it's really a balance of what sort of pressures on the outlet are you tolerant of. If that 20 psi rise is too much, like we talked with the gas chromatograph example, you may need a second regulator to then further reduce supply pressure effects further. Again, it's a balance between flow and supply pressure effect.
Okay. Here's a question about selecting the pressure of my gas system relief valve. How do I select the pressure?
Cool. Yeah, I can answer it right here, and I just advanced the slide so that hopefully it's intuitive. A relief valve is typically set at a pressure slightly above the low pressure level that we plan to operate at. As a general rule of thumb, and again, this is a very general rule, it might be 20% above our conventional low pressure set point. And that's all done to make sure that we have adequate headroom for that supply pressure effect, which is an inherent property and behavior of the internal physics of a pressure reducing regulator. So it is contingent upon a lot of things, but in general, it will be set above that low pressure operating space by some percentage. And it's, again, very case dependent.
Okay, I think we have time here for maybe one more question. Selecting a regulator for my app. How do I select a regulator for my application?
Wow, that's a really deep question, and that one is a definitely it depends type of answer. But the truth is it depends, and I'd highly recommend anybody that's looking for some assistance from a regulator selection to seek out your local Swagelok sales and service center. We've got people that specialize in this, like regional and global, and it's really useful. But I'll walk you through the general process that is involved when it comes to regulator selection. First and foremost, you need to know what function you're after. So is it a pressure reducing regulator or is it a back pressure regulator? Does it need to be domed or does it need a pilot regulator? Those types of foundational questions, like very high level. From there, regulator selection often involves then understanding the range of inlet pressures. And typically that max inlet pressure will dictate a lot of the nuances of the internal components that are paramount. From there, we can then select our targeted outlet pressure or anticipate what sort of outlet pressures we will endure given supply pressure effects and the like, right? So that's where the customers really needed details come in. From there, we can pick things like the flow rates, like we can observe the performance curves of a regulator to decide what sort of flow rates we can expect and compare that against customer needs. From there, we then would look into system compatibility from media. So knowing what type of medias are we at risk for embrittlement or how hazardous is the media. From that, we can also then, it influences the functionality that we need out of the regulator. For example, if we think that there's any risk of escapement through sensor element rupture, that diaphragm element, we may choose to integrate like a captured vent in our regulator. And then last but not least, we then go into picking the end connections and the mounting and all the other mechanical features of the regulator. Do I need a locking handle, for example? So it's a very systematic process that's well proven, and our sales and service centers are experts at making these selections.
All right, that's great. Thank you, Jeff, for sharing your expertise with us. Awesome presentation. We want to thank our audience for attending today's webcast. Again, thank you to Jeff and Swagelok for putting together this timely and informative presentation. An on-demand version of this webcast will be made available in the coming days and will be emailed to everyone. Again, thank you so much, Jeff, presenting to us today. And to our audience, have a great day. Thanks.